Hello! I have a question for you guys. Is it possible to have some function so that its area under the curve is the same as its arc length on any interval a, b? What do you guys think? And of course, we're talking about just the numerical value. We are not talking about their units or whatsoever, right? So, Teddy, what do you think? Yes. And of course, it's a yes, because otherwise, how can we make this video, right? So have a look right here, because it's actually really cool, and we'll end up with a differential equation, and we'll also see some function that you might not expect. So have a look. First, we want the area to be equal to arc length, and we have to know how to compute the area and also the arc length with integrations. So let me change this into an integration equation first. Because for area, it's just the integral going from a to b, f of x dx, but let me write f of x as y. You will see why, right? Alright, and for the arc length, of course we also have that formula, and I have the video already in the description for your convenience. Go check it out if you would like. But the formula for the arc length is the integral going from a to b, and we will have the square root, and then we will have 1 plus parentheses with dy dx right here, namely the derivative, and then you square that, and then we have the dx. So have a look right here. You see, both of them are integrating from a to b. Here we have y, here we have this. So if they are equal to each other inside, of course, when we integrate that, will be equal, right? And this is why I put on y right here, because this is how we get that differential equation. So again, we want to have this being equal to that. Let me just write down y has to be equal to the square root of 1 plus the first derivative square. So dy dx right here, and then square that. Now, how can we solve this differential equation? Well, we only have the dy dx right here. It would be a great idea if we isolate that part first. We can do so by first square both sides and then minus 1 both sides, and you will see that. Let me put this down first. dy dx, and when we square, right, that will be equal to y squared minus 1. All right, great. And then, because we have the second power here, we can just take the square root on both sides, and technically, again, the plus minus. But if you want to keep everything positive, you don't need a negative, right? So just get rid of negative out, then this will be okay. Because if you do have the negative, later on the function will be down below in the third and also the fourth quadrant. And if you just do the area with the integration, you end up with negative value. You can take the absolute value of that, but just keep the positive. It's much better. All right, so what we have, of course, is they cancel, and then we just get the dy dx. That's equal to the square root of y squared minus 1. Perfect. Multiply the dx on both sides and divide this on both sides. It looks like we have the 1 over square root of y squared minus 1 with the dy. And this is equal to the dx right here. Then we can just integrate both sides. Very nice, huh? So integrate, integrate. How would you integrate this though? Yes, you can do the u substitution with some trig functions. Trig sub, technically. But life does not have to be that hard sometimes if you know some hyperbolic functions. Have a look. Let me write this down right here for you guys. Notice, if we differentiate with respect to some variable, let's just put on t because I used x and y over there already. But if we differentiate the inverse, not cosine, not whatever, but the hyperbolic version of the cosine. So it's the cosh, right? Inverse cosh, and I'm using t for the input, like this. If we differentiate this, in fact, we get 1 over square root of t squared minus 1, which is very nice. Because if we integrate this, we just get inverse cosh, right? So that's exactly what we'll get on the left-hand side. This will give us inverse cosh of y, and don't worry about the plus e, you can just put on the plus e on the right hand side. Integrating dx, you just get x, but don't forget the plus e now. Well, if you want to figure out the function, you can just take the original cosine with the h on both sides, namely cos. So you get y is nicely equal to cos of x plus c, like this. And in fact, you can pick whatever c that you want because this is actually just going to be a horizontal shiftment. And I know cos does not look like this, but that was just a random picture, right? But have a look right here on the screen. Take a look if you have c is equal to 0. Very cool, huh? So this right here is actually the answer. Well, it was very unexpected, right? But you know, gosh, the hyperbolic functions, they're actually really cool. So don't be like, oh man, I have to learn some new functions by the end of the Cal 2 semester. Don't be like that. You know, there are some really cool stuff. Anyway, if you know some other cool properties with like cos or sinh, leave a comment down below and let us know, right? And I'll see you guys in the next video. Bye!